The cosmic neutrino background, CNB, also known as the relic neutrino background, is a fascinating and fundamental aspect of cosmology. It consists of low-energy neutrinos that pervade the universe, originating from the early moments after the Big Bang. Let's delve into the details. 1. Origin and formation. The CNB was formed approximately 1 second after the Big Bang, during a period when the universe was extremely hot and dense. At this time, the universe was filled with a plasma of particles, including neutrinos, electrons, positrons, and photons, all in thermal equilibrium. As the universe expanded and cooled, the temperature dropped to about 2.5 MeV, million electron volts, causing neutrinos to decouple from the rest of the matter. 12. 2. Decoupling and temperature. When neutrinos decoupled, they stopped interacting with other particles and began to travel freely through space. This decoupling occurred much earlier than the decoupling of photons, which formed a cosmic microwave background, CMB, when the universe was about 379,000 years old. The CNB, therefore, provides a snapshot of the universe at a much earlier stage. 13. The temperature of the CNB today is estimated to be around 1.95 K, slightly cooler than the CMB, which is about 2.725 K. This difference arises because the universe continued to expand and cool after the neutrinos decoupled. 13. 3. Properties of neutrinos. Neutrinos are incredibly light and weakly interacting particles. They come in 3 flavors: electron neutrinos, muon neutrinos, and tau neutrinos. These flavors can oscillate, meaning they can transform into one another as they travel. Neutrinos are also unique because they might be their own antiparticles, a property known as being Majorana particles. 23. 4. Detection challenges. Detecting the CNB is extremely challenging due to the very low energy of these neutrinos, which is around 10⁻⁻⁴ to 10⁻⁻⁶ eV. Even high-energy neutrinos are notoriously difficult to detect, and the CNB neutrinos have energies about 10⁻⁻10 times smaller. As a result, direct detection of the CNB may not be feasible for many years, if at all. 12. 5. Indirect evidence and importance. Despite the difficulty in direct detection, there is strong indirect evidence for the existence of the CNB. Big Bang cosmology predicts the CNB, and its effects can be inferred from observations of the CNB and the large-scale structure of the universe. The CNB plays a crucial role in our understanding of the early universe, providing insights into the conditions and processes that occurred shortly after the Big Bang. 12. 6. Cosmological significance. The CNB is significant for several reasons. Early universe conditions. It offers a glimpse into the state of the universe when it was just 1 second old. Neutrino properties. Studying the CNB can help us understand the properties of neutrinos, including their masses and how they interact with other particles. Cosmological models. The CNB is an essential component of the Standard Cosmological Model (CDM), which describes the evolution and structure of the universe. 23. In summary, the cosmic neutrino background is a relic from the early universe, providing valuable information about the conditions and processes that shape the cosmos. Although direct detection remains a challenge, the CNB continues to be a vital area of research in cosmology. Neutrinos interact with matter primarily through the weak nuclear force, which is one of the 4 fundamental forces in nature. This interaction is incredibly weak compared to electromagnetic and strong nuclear forces, making neutrinos notoriously difficult to detect. Here's a detailed look at how these interactions occur. 1. Types of interactions. Neutrinos interact with matter via 2 main processes: charged current (CC) interactions. In this type of interaction, a neutrino exchanges a W boson with a particle, resulting in the transformation of the neutrino into its corresponding charged lepton. For example, an electron neutrino becomes an electron. For example, E and Ne plus P. Here, an electron neutrino \_e interacts with a neutron, N, producing an electron, E and a proton, P. 12. Neutral current (NC) interactions. In this interaction, a neutrino exchanges a Z boson with a particle, but the neutrino remains a neutrino. For example, nu plus N. Here, a neutrino \_nu interacts with a nucleon, N, and both the neutrino and nucleon remain unchanged. 12. 2. Interaction cross-section. The probability of a neutrino interacting with matter is described by its cross-section, which is extremely small. For high-energy neutrinos, the cross-section increases, but it remains much smaller than that of other particles. This small cross-section is why neutrinos can pass through vast amounts of matter without interacting. 13. 3. Detection methods. Despite their weak interactions, neutrinos can be detected using large and sensitive detectors. Some common methods include water Cherenkov detectors. These detectors use large volumes of water to detect the Cherenkov radiation produced when a neutrino interacts and produces a charged particle moving faster than the speed of light in water. Scintillation detectors. These use materials that emit light when a neutrino interaction occurs, which is then detected by photomultiplier tubes. Liquid argon detectors. These detect ionization electrons produced by neutrino interactions in liquid argon-13. For matter effects. When neutrinos travel through matter, their effective mass can change due to interactions with the particles in the medium. This phenomenon, known as the Mikheyev-Smirnov-Wolfenstein (MSW) effect, can alter the oscillation behavior of neutrinos, affecting how they transform from one flavor to another. 5 applications and importance. Understanding neutrino interactions is crucial for several reasons. Astrophysics. Neutrinos provide information about processes in the Sun, supernovae, and other cosmic events. Particle physics. Studying neutrino interactions helps us understand fundamental properties of particles and forces. Cosmology. Neutrinos play a role in the evolution of the universe and can provide insights into its early moments. 12. In summary, neutrinos interact with matter through weak nuclear interactions, primarily via charged and neutral current processes. Despite the challenges in detecting them, these interactions provide valuable information across various fields of physics. Neutrinos are fascinating elementary particles that come in 3 different types, or flavors, each associated with a corresponding charged lepton. Here's a detailed look at the different types of neutrinos. 1. Electron neutrino /nu_e. Associated lepton, electron, E caret. Discovery. The electron neutrino was the first type of neutrino to be discovered. It was proposed by Wolfgang Pauli in 1930 to explain the missing energy in beta decay and was experimentally confirmed by Clyde Cohen and Frederick Reyners in 195612. Characteristics. Electron neutrinos are produced in nuclear reactions, such as those in the Sun, nuclear reactors, and during beta decay processes. 2. Muon neutrino /nu_/mu. Associated lepton, muon /mu caret. Discovery. The muon neutrino was discovered in 1962 by Leon Lederman, Melvin Schwartz, and Jack Steinberger, who were awarded the Nobel Prize in Physics for this discovery. 12. Characteristics. Muon neutrinos are produced in high-energy processes, such as cosmic ray interactions in the atmosphere and particle accelerators. 3. Tau neutrino /nu_/tau. Associated lepton, tau caret. Discovery. The tau neutrino was the last of the 3 neutrino types to be discovered. It was confirmed by the Dormut direct observation of the new tau collaboration in 2012. Characteristics. Tau neutrinos are produced in processes involving the tau particle, which is much heavier than the electron and muon. 4. Antineutrinos. Definition. Each type of neutrino has a corresponding antiparticle known as an antineutrino. For example, the electron antineutrino /bar/nu_e is the antiparticle of the electron neutrino. Characteristics. Antineutrinos are produced in processes such as beta decay, where a neutron decays into a proton, an electron, and an electron antineutrino. 5. Sterile neutrinos, hypothetical. Definition. Sterile neutrinos are a hypothesized type of neutrino that do not interact via the weak nuclear force, only through gravity. They are not part of the standard model of particle physics. Characteristics. If they exist, sterile neutrinos could help explain certain anomalies in neutrino experiments and might be a component of dark matter. 23. 6. Neutrino oscillations. One of the most intriguing properties of neutrinos is their ability to oscillate between different flavors as they travel. This means an electron neutrino can transform into a muon neutrino or a tau neutrino and vice versa. This phenomenon was first confirmed in experiments observing solar and atmospheric neutrinos and has profound implications for our understanding of particle physics. 12. Summary. Electron neutrino /nu_e associated with electrons, discovered in 1956. Muon neutrino /nu_/mu associated with muons, discovered in 1962. Tau neutrino /nu_/tau associated with taus, discovered in 2000. Antineutrinos, antiparticles of neutrinos, produced in various decay processes. Sterile neutrinos, hypothetical neutrinos that interact only through gravity. Neutrinos are essential for understanding fundamental processes in the universe, from nuclear reactions in stars to the behavior of particles at the smallest scales. Neutrino oscillations are a fascinating quantum mechanical phenomenon where a neutrino created with a specific flavor, electron, muon, or tau can later be detected as a different flavor. This process implies that neutrinos have mass and that the flavor states are not the same as the mass states. Here's a detailed explanation of how neutrino oscillations work. 1. Flavor and mass eigenstates. Neutrinos are produced and detected in specific flavor states, \nu_e, \nu_mu, \nu_tau, but these flavor states are quantum superpositions of mass eigenstates, \nu_1, \nu_2, \nu_3. The relationship between flavor and mass eigenstates is described by the Pontikova-Makinekigawasekata (PMNS) matrix 12. 2. Quantum superposition. When a neutrino is produced, it is in a specific flavor state, which is a combination of mass eigenstates. As the neutrino travels, these mass eigenstates propagate with different phases due to their different masses. This difference in phase causes the superposition to change over time, leading to a change in the probability of detecting a particular flavor. 12. 3. Mathematical description. The probability of a neutrino changing from one flavor to another as it travels is given by the oscillation formula. P equals 4I J sigma UI adjacent to 4 image 2L, where P \nu_alpha \right arrow \nu_ beta is the probability of a neutrino of flavor \alpha changing to flavor \beta. U_\alpha I are elements of the PMNS matrix. \delta M_ij(2) is the difference in the squares of the masses of the mass eigenstates I and j. L is the distance traveled by the neutrino. E is the energy of the neutrino. 13. For experimental evidence, neutrino oscillations were first confirmed by observing the deficit of solar neutrinos, known as the solar neutrino problem. Experiments like the Sudbury Neutrino Observatory (SNO) and Superchemicandy provided clear evidence of neutrino oscillations by detecting changes in neutrino flavors. 12. 5. Matter effects (MSW effect). When neutrinos travel through matter, their oscillation behavior can be affected by interactions with electrons in the medium. This is known as the Mikheyev-Smirnov-Wolfenstein (MSW) effect. It can enhance or suppress oscillations depending on the density of the matter and the energy of the neutrinos. 13. 6. Implications. Neutrino oscillations have profound implications for our understanding of particle physics and cosmology. Neutrino mass. The observation of neutrino oscillations implies that neutrinos have mass, which was not accounted for in the original standard model of particle physics. Lepton flavor violation. Neutrino oscillations demonstrate that lepton flavor is not conserved in neutrino propagation. Cosmology. Neutrinos play a role in the evolution of the universe, and their masses and mixing parameters are important for understanding the large-scale structure of the cosmos. 12. In summary, neutrino oscillations are a quantum mechanical process where neutrinos change flavors as they travel, due to the differences in their mass eigenstates. This phenomenon has been confirmed by various experiments and has significant implications for our understanding of fundamental physics. Neutrino oscillations play a significant role in the behavior and detection of neutrinos emitted from supernovae. Here's a detailed explanation of how these oscillations affect supernova neutrinos. 1. Production of supernova neutrinos. During a core collapse supernova, a massive star's core collapses, leading to the emission of an enormous number of neutrinos. These neutrinos are produced in all three flavors, electron, muon, and tau neutrinos, and their corresponding antineutrinos. 12. The energy released in the form of neutrinos carries away about 99% of the gravitational energy of the collapsing star. 1. 2. Neutrino oscillations in dense environments. In the dense environment of a supernova, neutrino oscillations are influenced by several factors: matter effects, MSW effect. As neutrinos travel through the dense matter of the supernova, their oscillation probabilities are affected by interactions with electrons. This is known as the Mikheyev-Smirnov-Wolfenstein (MSW) effect, which can enhance or suppress oscillations depending on the density and composition of the matter. 12. Neutrino-neutrino interactions. In the supernova core, the density of neutrinos is so high that neutrino-neutrino interactions become significant. These interactions can lead to collective oscillation phenomena, where neutrinos oscillate in a correlated manner. 34. 3. Collective oscillations and flavor instabilities. Collective oscillations can result in complex flavor transformations among neutrinos. Some key phenomena include synchronized oscillations. Neutrinos can oscillate in a synchronized manner due to their mutual interactions. Bipolar oscillations, these occur when there is a significant difference in the number of neutrinos and antineutrinos, leading to rapid flavor conversions. Spectral splits and swaps, the energy spectra of different neutrino flavors can split or swap due to collective effects. 34. 4. Impact on supernova dynamics. Neutrino oscillations can influence the dynamics of the supernova explosion, energy transport. The flavor transformations can affect how energy is transported out of the supernova core, influencing the explosion mechanism. Nucleosynthesis, the changing neutrino flavors can impact the synthesis of heavy elements in the supernova environment. 34. 5. Detection of supernova neutrinos. The oscillations of supernova neutrinos affect their detection on Earth. Flavor composition. By the time supernova neutrinos reach Earth, their flavor composition has been altered by oscillations. Detectors designed to capture specific neutrino flavors must account for these changes. Signal interpretation. Understanding the oscillation effects is crucial for interpreting the neutrino signal from a supernova, which provides insights into the explosion mechanism and the properties of neutrinos. 12. Summary. Neutrino oscillations in supernovae involve complex interactions and transformations influenced by the dense environment and collective effects. These oscillations play a crucial role in the dynamics of the explosion and the detection of neutrinos on Earth, providing valuable information about both the supernova and the fundamental properties of neutrinos. Supernova neutrinos are produced in vast quantities during a core collapse supernova, where a massive star's core collapses and emits neutrinos of all flavors. Here's a detailed look at the different types of supernova neutrinos. 1. Electron neutrinos, /nu_e, and electron antineutrinos, /bar/nu_e. Production. Electron neutrinos are primarily produced during the neutronization phase, where protons and electrons combine to form neutrons and electron neutrinos. Electron antineutrinos are produced in processes like beta decay. Detection. These neutrinos are often detected via inverse beta decay in detectors like water Cherenkov detectors and liquid scintillation detectors. 12. 2. Muon neutrinos, /nu_/mu, and muon antineutrinos, /bar/nu_/mu. Production. Muon neutrinos and their antineutrinos are produced in the core collapse supernova through processes involving pion decay. Detection. These neutrinos are harder to detect directly because their energies are typically below the threshold needed to produce muons in detectors. 12. 3. Tau neutrinos, /nu_/tau, and tau antineutrinos, /bar/nu_/tau. Production. Tau neutrinos and their antineutrinos are also produced in the core collapse supernova, but like muon neutrinos, they are less likely to be detected directly due to their high energy thresholds. Detection. Direct detection of tau neutrinos is challenging because the energies required to produce tau particles are very high. 12. 4. Neutrino emission phases. Supernova neutrinos are emitted in different phases during the collapse and explosion. Neutronization burst. A brief burst of electron neutrinos occurs as the core collapses and protons are converted into neutrons. Accretion phase. During this phase, neutrinos of all flavors are emitted as matter falls onto the protoneutron star. Cooling phase. The protoneutron star cools by emitting neutrinos of all flavors over tens of seconds. 12. 5. Energy spectrum. The energy of supernova neutrinos typically ranges from 10 to 30 MeV. The energy distribution can provide insights into the processes occurring within the supernova and the properties of neutrinos. 13. 6. Detection and importance. Detecting supernova neutrinos is crucial for understanding the mechanisms of supernova explosions and the properties of neutrinos. The detection of neutrinos from SN 1987 have provided valuable data that confirmed theoretical models of supernovae. 12. In summary, supernova neutrinos come in all three flavors, electron, muon, and tau, and their corresponding antineutrinos. They are emitted in different phases during the supernova explosion and have a wide range of energies. Detecting these neutrinos helps us understand both the supernova mechanisms and the fundamental properties of neutrinos. Supernova neutrinos play a crucial role in the process of nucleosynthesis, which is the formation of new atomic nuclei from pre-existing nucleons, protons, and neutrons. Here's a detailed look at how supernova neutrinos contribute to nucleosynthesis. 1. Neutrino-driven wind. After the core collapse of a massive star, a protoneutron star is formed, and it emits an enormous number of neutrinos. These neutrinos drive a neutrino wind, which is a flow of matter from the surface of the protoneutron star. This wind is rich in protons and neutrons and provides the conditions necessary for nucleosynthesis. 2. Neutrino processes in nucleosynthesis. Several key processes involving neutrinos contribute to nucleosynthesis in supernovae. The \nu process, neutrinos interact with nuclei in the outer layers of the star, inducing reactions that produce certain isotopes. For example, neutrino interactions can produce isotopes like 11b, 19f, 138 La, and 180 tar-12. The \nu process, in proton-rich environments, neutrinos can convert protons into neutrons, enabling the synthesis of heavier elements. This process is particularly important for producing certain proton-rich isotopes. 12. The R process, the rapid neutron capture process, R process, occurs in environments with a high density of neutrons. Neutrinos can influence the neutron-to-proton ratio, affecting the conditions for the R process. This process is responsible for creating about half of the heavy elements beyond iron, including gold and uranium-13. 3. Flavor oscillations and matter effects. Neutrino flavor oscillations and interactions with matter can alter the flux and energy spectra of neutrinos, impacting nucleosynthesis. For example, the Mikheyev-Smirnov-Wolfenstein (MSW) effect can enhance or suppress certain neutrino interactions, thereby influencing the production of specific isotopes. 13. 4. Impact on supernova dynamics. Neutrinos carry away most of the energy released during a supernova explosion. This energy transport is essential for driving the explosion and for the subsequent nucleosynthesis in the ejected material. The interactions of neutrinos with matter help to heat and eject the outer layers of the star, where nucleosynthesis occurs. 12. Summary. Supernova neutrinos are integral to nucleosynthesis through processes like the \nu process, \nu-p process, and R process. They influence the production of various isotopes and play a critical role in the dynamics of the supernova explosion, affecting the conditions under which nucleosynthesis occurs. Supernova neutrinos contribute to the production of several key isotopes through various nucleosynthesis processes. Here are some of the notable isotopes produced. 1. 7 Li, lithium-7. Production. Neutrino interactions with helium nuclei can produce 7 Li. This isotope is important for understanding the chemical evolution of galaxies. 12. 2. 11 B, boron-11. Production. Neutrino-induced reactions on carbon and nitrogen nuclei can lead to the formation of 11 B. This isotope is significant for studying cosmic ray spallation processes. 12. 3. 19 F, fluorine-19. Production. Neutrino interactions with near nuclei can produce 19 F. This isotope is relatively rare and provides insights into stellar nucleosynthesis. 12. 4. 138 La, lanthanum-138. Production. Neutrino interactions with barium nuclei can produce 138 Lane. This isotope is important for understanding the S process and R process nucleosynthesis. 12. 5. 180 Tar, tantalum-180. Production. Neutrino interactions with hafnium nuclei can produce 180 Tar. This isotope is unique because it exists in a long-lived metastable state, making it useful for studying nucleosynthesis in supernovae. 12. 6. 92 Mo, molybdenum-92. Production. Neutrino-driven winds in supernovae can produce 92 Mo. This isotope is part of the P process, which involves proton-rich nucleosynthesis. 3. Summary. These isotopes are produced through various neutrino interactions and nucleosynthesis processes in the extreme environments of supernovae. Studying these isotopes helps scientists understand the mechanisms of supernova explosions and the chemical evolution of the universe. Neutrinos interact with nuclei through weak nuclear interactions, leading to the production of various isotopes. Here's a detailed explanation of how these interactions occur. 1. Types of neutrino interactions. Neutrinos interact with nuclei via two main processes: charged current (CC) interactions. In these interactions, a neutrino exchanges a W boson with a nucleon, proton or neutron, resulting in the transformation of the neutrino into its corresponding charged lepton. For example, an electron neutrino becomes an electron. This process can change a neutron into a proton or vice versa, leading to the production of different isotopes. For example, E and Ne plus P. Here, an electron neutrino \nu_e interacts with a neutron, N, producing an electron, E caret, and a proton, P12. Neutral current, NC, interactions. In these interactions, a neutrino exchanges a Z boson with a nucleon, but the neutrino remains a neutrino. This process can excite the nucleus, leading to the emission of particles such as neutrons, protons, or alpha particles, which can then produce different isotopes. For example, nu plus N. Here, a neutrino \nu interacts with a nucleus, N, exciting it to a higher energy state, N*12. 2. Neutrino-induced nucleosynthesis processes. Several key processes involving neutrino interactions contribute to nucleosynthesis in supernovae and other astrophysical environments. The \nu process, neutrinos interact with nuclei in the outer layers of a supernova, inducing reactions that produce certain isotopes. For example, neutrino interactions with carbon and nitrogen can produce (11b, boron-11, and (19f, fluorine-19, 23). The \nu-p process, in proton-rich environments, neutrinos can convert protons into neutrons, enabling the synthesis of heavier elements. This process is particularly important for producing certain proton-rich isotopes 23. The R process, the rapid neutron capture process, R process, occurs in environments with a high density of neutrons. Neutrinos can influence the neutron-to-proton ratio, affecting the conditions for the R process. This process is responsible for creating about half of the heavy elements beyond iron, including gold and uranium-23. 3. Experimental evidence and detection. Detecting neutrino interactions with nuclei is challenging due to the weak nature of these interactions. However, experiments using large detectors, such as water Cherenkov detectors and liquid scintillation detectors, have provided valuable data. For example, the detection of neutrinos from supernova SN 1987 are confirmed theoretical models of neutrino-induced nucleosynthesis. 12. Summary: neutrinos interact with nuclei through charged and neutral current interactions, leading to the production of various isotopes. These interactions play a crucial role in nucleosynthesis processes in supernovae and other astrophysical environments, contributing to the formation of elements beyond iron. Supernova 1987 SN 1987 is one of the most significant astronomical events of the 20th century. It has had a profound impact on our understanding of supernovae, neutrinos, and nucleosynthesis. Here's a detailed look at SN 1987 and its contributions to science. 1. Discovery and observations. SN 1987 was first observed on the 23rd of February 1987 in the Large Magellanic Cloud, a nearby dwarf galaxy. It was the closest supernova observed in nearly 400 years, making it an unprecedented opportunity for detailed study. 12. The supernova was visible to the naked eye and was extensively observed across the electromagnetic spectrum, from radio waves to gamma rays. 12. 2. Neutrino detection. One of the most groundbreaking aspects of SN 1987 was the detection of neutrinos. About 2 hours before the visible light from the supernova was observed, 3 neutrino observatories, Kamiakan D2, IMB, and Baksan, detected a burst of neutrinos. 23. This was the first direct evidence of neutrinos from a supernova, confirming theoretical predictions about core collapse supernovae and the role of neutrinos in these events. 3. Nucleosynthesis insights. SN 1987 provided critical insights into the process of nucleosynthesis, particularly the production of heavy elements. Key findings include neutrino-induced nucleosynthesis. The detection of neutrinos confirmed their role in driving nucleosynthesis processes, such as the \nu process, where neutrinos interact with nuclei to produce isotopes like (11b) and (19f14). R process, the supernova environment, rich in neutrons, provided conditions for the rapid neutron capture process, R process, responsible for creating many of the heavy elements beyond iron. 4. For supernova dynamics and explosion mechanism. The detailed observations of SN 1987 helped refine models of supernova dynamics and the explosion mechanism. Shockwave propagation. The light curves and spectra provided information about the shockwave propagation through the star's layers, helping to understand the energy release and material ejection. 12. Progenitor star. SN 1987's progenitor was identified as a blue supergiant, which was unusual since most Type II supernovae progenitors are red supergiants. This finding prompted revisions in stellar evolution models 12. 5. Long-term observations. SN 1987 continues to be observed, providing ongoing insights into supernova remnants and the late stages of stellar evolution. The interaction of the supernova shockwave with the surrounding circumstellar material has been studied extensively, revealing details about the progenitor star's mass loss history. 12. Summary. SN 1987 has significantly advanced our understanding of supernovae, neutrino physics, and nucleosynthesis. The detection of neutrinos confirmed their critical role in supernova dynamics and nucleosynthesis processes, while the detailed observations of the explosion and its aftermath have refined models of stellar evolution and supernova. Goodbye.